Today, our team will present our project titled Not All Video Become Outdated. Short video recommendation by learning to deconfound release interval bias or LDRI. Our goal is to address a common problem in recommendation systems, that of recommending only the latest videos, and show how we can make recommendations fairer and more relevant to user interests. Recommended systems are essential on digital platforms. They analyze user behavior preferences and interaction data to recommend content that users are likely to enjoy. You have seen them on platforms like YouTube, TikTok, and Netflix, where recommendations drive user engagement by providing relevant content. But with this power comes a responsibility. How do we ensure balanced recommendations that don't overfocus on recent or trending items, allowing for a richer, more diverse experience? Let's talk about bias in recommender systems. One of the most biggest challenges in recommender systems is bias. Today we'll focus on three types. First is release interval bias. Many systems prefer recent content, while older but high quality videos go unseen. Second is popularity bias, which is content with more views tends to dominate recommendations. Third is duration bias. Videos of certain lengths may be promoted over others, leading to imbalances. This bias limits content discovery as users end up seeing a small fraction of available material. Next is problems with existing methods. Current solutions like survival analysis aim to adjust for these biases but aren't ideal. For example, survival analysis can adjust for item aging but can't determine if a video remains relevant over time. These methods treat all videos the same, leading to a general bias favoring newer content. Therefore, we need a model that only recognizes the release interval bias but also addresses each video's unique characteristics and ongoing relevance. Our research goal is straightforward. Develop a recommendation method that can understand and incorporate each video's unique recency sensitivity. In other words, instead of merely focusing on the release date, our model will consider whether a video remains relevant and interesting over time.
Introducing the LDRI model. We present the LDRI model, learning to deconfound release interval bias. LDRI has two main components. First, user video matching. This part predicts how well a video matches a user's preferences based on features and interaction history. Second is recency sensitivity. This component assesses how a video's relevance changes over time, accounting for the natural decay or sustained interest in certain content. LDRI uses causal inference to separate relevance from mere age, ensuring fair recommendations that prioritize meaningful content. Causal inference in LDRI. To achieve this, LDRI relies on causal inference. Causal inference allows us to distinguish factors that genuinely impact user interest from those that create misleading connections, like video age. With causal inference, we can filter out artificial connections to user interest and video age, making sure our model's recommendations are based on relevance and not on bias. An essential part of this is backdoor adjustment, a causal technique LDRI uses to block non-causal paths. By blocking the path between video age and recommendations, we ensure that the recommendations are based on the true relevance of content separated from bias introduced by its release interval. Talking about mathematical backdoor adjustment, we use a formula called backdoor adjustment. This formula adjusts the recommendation outcomes, reweighting them so that the release interval does not influence them. As a result, we can base recommendations on the relevance of each video. Our LDRI model has two main parts. First is matching model. This model measures how relevant a video is to a user's interest. Secondly is recency sensitivity perceptron. This perceptron measures if a video remains interesting over time, independently of its release date. The two parts work together to help LDRI overcome release interval bias, delivering balanced recommendations regardless of video age.
Now let's talk about how did we train this model. LDRI uses a joint learning framework by training both the matching model and the recency sensitive perceptron together. LDRI balances between relevance and time sensitivity. These approaches allow the model to provide recommendations that are relevant and fairly considered content from various release dates. So the training loss include L of M, the binary cross entropy loss for matching relevance, and L of T, the loss for recency sensitivity, which adjusts based on the positive feedback from neighboring intervals. By optimizing both the losses together, LDRI can better recommend content based on both relevancy and recency, addressing the problem of bias. Now let's talk about the experimental and evaluation setup. So the dataset contains the queer pure and queer 1K, which contain user interactions data over various releases intervals. Our key metrics are recall at K and NDCG at K, which is normalized discounted cumulative gain, map at K, mean average precision, and HR at K, which contain hit rate. These metrics assess the quality of a recommendation testing if LDRI provides fair, relevant, and balanced content. Now let's talk about the performance result and analysis. The baseline models also contain the deep FM, NFM, and AFM. This served as a baseline to gauge LDRI's performance, particularly its ability to overcome release interval bias. These comparisons provide insights into where LDRI has improved on traditional recommendation models. Now let's talk about the performance results and analysis. LDRI showed significant improvements over the baseline model, especially when it comes to release interval bias. Overall performance include LDRI consistently delivered high quality recommendation across various metrics. The model also effectively adapted to new videos even with limited data. LDRI also remains stable across different release intervals, showing its robustness and effectiveness in addressing biases. Here we can see some performance graph. The NDCG at K matrix is shown here, and you will notice that LDRI consistently outperform baseline models across release intervals. This is critical because it proves LDRI's advantage in delivering relevant recommendation for both newer and older videos, effectively balancing bias and user relevance. Okay, let's talk about the conclusions and future work. To conclude, LDRI successfully mitigates release interval biases in short video recommendations, providing a fairer and more inclusive experience. Using causal inference, LDRI focuses on genuinely relevant recommendation, helping users see diverse content regardless of release date. LDRI's design also allows it to be integrated with existing system, making it adaptable for widespread use. The future work include dynamic user interest modeling, where we could improve user satisfaction by adapting LDRIs to users' changing preference. Testing LDRI on other media like music or articles could show its versatility and adaptability to different domains. These steps could help expand LDRI's impact beyond just video platforms.
Thank you.
Thank you.